All right, so we are going to start with titration of a weak acid and a strong base today. There is a lecture checkup quiz that will be due by tomorrow, and I'll show you that at the end of lecture. So we have a lecture checkup quiz due by tomorrow. Don't forget you've got your Chem 101 homework and then another quiz on Monday. So today's lecture, I think, is probably the most difficult lecture of all of Chem 229. So it's super important if you're watching this now live with me, or if you're watching it later, you need to make sure you stop me at any point when you don't understand. If you're watching it later, make sure you pause it and go, wait, where, what? And then come back again and make sure your questions are answered. Because this is the lecture where we put every single thing into one single problem. Everything we've learned in Chem 229 is now going to coincide in one single problem. All right, so if you're missing any pieces, it gets really exposed here, right? So we're going to start with the titration of a weak acid and a strong base. And again, if you're watching this live, just feel free to interrupt me at any time and go, wait, what? I don't know, where are you? What? And if you're watching it later, make sure you pause it, get your questions answered. You can even send me a text, if whatever you need to do. But this is the lecture, like I said, where everything we've learned all comes in together in one single problem. And you're going to see on your lecture quiz how that works. Okay, so we're going to start. And again, key, ask questions. Okay, so we did a titration with a strong acid and a strong base last time. I skipped the problem that's the same problem, it's just opposite. I'll post it when we finish this lecture. It's almost exactly the same. But I want to spend a lot of time and go very slowly on these titrations with a weak acid and a strong base, and a strong acid with a weak base. Okay, so when we titrate a weak acid with a strong base, our equivalence point is not 7, right? It's only 7 if we have a strong acid and a strong base. So the initial pH, we're going to, so when we do this, we're going to have our weak acid is going to be in our beaker or in our flask. Our strong base is what we're going to be adding to it. So initially, when we haven't added anything, we only have our weak acid. And so therefore, if we want to know the initial pH, we do that using our process for pHs of weak acids, using our Ka, our ice table, etc. Now, the pH in the excess acid region is determined in a buffer. So after we've added a little bit of base, now we've got conjugate acid and we have our weak acid. So now we've got a buffer, right? The pH at the equivalence point, so this one we're going to talk about, is we're going to be using finding our pH using the Kb of the conjugate base with the weak acid. And then after the equivalence point, it's going to be excess strong base, and that's just going to be, we're just going to use pH of a strong base. So you can see here's pH of weak acid, here's Henderson-Hasselbalch buffers, here's pH of a weak base, and then here's pH of a strong base, right? So there's four different types of problems all in one, right? This is where these problems are a lot. So here's what I suggest you do. When you're doing a titration, the most important thing is you need to know, where are we on our titration? Are we initial pH? Are we before the equivalence point? Are we at the equivalence point, or are we after the equivalence point, right? You have to know where you are in the titration. That is number one on getting these problems correct. Where are we on the titration? Now, how can you tell? You got to look at your moles, and we're going to talk about that today. So remember, at the equivalence point, moles of acid equals moles of base. So that's how you know you're at your equivalence point. And then we're going to keep going with the rest of them. And I'm going to go slowly. Again, ask questions as you go. This is kind of a lot. I put this here, look, yellow, highlighted, going, hey, here's how you do this part. By the way, my office is hotter than the lab. It must be 100 degrees in here. So if I get heat stroke and pass out, you know why. Okay, so first of all, We're going to do a titration of 25 milliliters of 0.1 molar of our hot show with 1.1 molar NaOH. Okay, so what are we doing? Okay, so we're going to add these two together. What's that make? So if you add, again, equations, knowing the chemistry is the key. If we have HCHO2, that's the same as HA, right? Plus, we're going to add NaOH to it. So we've got our little, I'm just gonna do a beaker because I can't draw. I mean, look, I can't even draw a beaker. And we're gonna add NaOH to it. So we have our acid here, and we're gonna add NaOH to it. So add NaOH to it. So what's that gonna make? Again, when we do this, it's just like the same thing as like adding a base. So we're going to make, I'm just gonna do a regular double displacement reaction. Acid plus base makes salt and water, right? I'm gonna lose my, so I have Na goes with CHO2, right? NaCHO2 plus HOH, which HOH is just, everybody okay if I say water. So now, this is kind of our basic of our whole reaction, but there's gonna be a bunch of other reactions that are involved here. So let's go through all of these now. I'm sure yes, here we are. Okay, so before anything has happened, what's our initial pH? So what's the pH in my beaker with my HA? So the pH in my beaker, in my HA, so if all I have is weak acid in here, then I just find the pH of weak acid. This is exactly what we did in your quiz, like your last quiz. This was it, finding the pH of weak acid, because all we have is weak acid. So we use K, X squared over whatever. Yeah, so minus X minus X. Okay, so our formula is going to be 1.8 times 10 to the negative 4. By the way, that's Ka. I think I've just memorized it, to be honest. For this one, equals X squared over 0.1. I'm going to assume X is small. At this point, I'm assuming these ice tables should be like magic in your brains. Then we just solve for X. Multiply by 1, multiply by 1, take the square root, X equals 4.24 times 10 to the negative 3, which is our H2O plus, right? That's our X. Okay, so then we take the negative log. I'll rewrite it for you. The negative log of 4.24 times 10 to the negative 3, and that equals 2.37, and that's our pH. Of course, we need to check our X is small. Again, our X is small is whatever we got, so 4.24 times 10 to the negative 3, that's our X, so our X is our H2O is this over original, 0.1 times 100, difference is 0.2, so it should work. 4.2%. Yes. Remember, we need to make sure this number is less than 5%. If it's not less than 5%, then we have to go and do the successive approximations or the quadratic formula, right? That was the question that was on your quiz, right? That a bunch of people forgot to do. I guarantee you it's going to come back on your quiz again and definitely on your exam. Okay, so initial pH of a weak acid, strong base. You find the initial pH by doing the Ka of a weak acid, right? Like this question right here, that was what's on your quiz. Now it's just part 1 of a problem. Oh, there's everything, really, really neat. Okay, same exact things, just prettier. Okay, now, what about if we add a little bit of base? So we've got this, actually I'm gonna do it on the next page. What about if we add a little bit of base? So we've got our weak acid in here and we add just a little bit of OH, just a little bit of base. Okay, so in that case, here we are adding a little bit of OH. We need to figure out, and this is what I mean by the moles, okay? We need to figure out where the equivalence point is. Okay, how do we find where the equivalence point is? We find the moles of that weak acid. That's the thing here. I'm going to just put HA. We need to find the moles of that because remember, the equivalence point is when moles of acid equal moles of base, right? And so remember, liters times molarity equals moles. So we just change this to liters, put in our molarity. This is our moles. When our moles of our acid equal the moles of our base, then we're at the equivalence point. So this is the number we're going to always come back to because that's our equivalence point. If we have more acid than base, we have excess acid. If we have more base than acid, we have excess base, right? So now we're going to add 5 milliliters. 5 milliliters. Okay, I'm going to add 5 milliliters. Okay, so if we add 5 milliliters of NaOH, we need to go, okay, so do we have the same amount of moles? Do we have more moles or do we have less moles than our acid? Again, how do we find moles? Molarity times liters equals moles, right? So we have 5 milliliters, which is, I don't know, 5 times 10 to the minus 3 liters. That's the way I do it. It makes my life easier. Times our molarity, which is 0.1 moles of NaOH over liters. This gives us moles. Again, so we have 5 times 10 to the negative 4 moles. So we compare this number, that's our moles of OH, and we compare it to the moles of our HA. It's less, right? We have less moles of our base than we do our acid. Okay, that means we are before our equivalence point. When it's equal, we're added. It's not equal, it's less. We're before our equivalence point. The pH in the excess acid region is determined as you would determine the pH of a buffer. Okay. Again, how do we know? I'm going to show, I have this right here. Really neat. Here's my neater. Here it is. This is the exact same thing. Because we have less base than we do acid, that means we have both conjugate and weak acid. We have both. And so now, this is what, for example, what your quiz will be on Monday is what's the pH of a buffer? Okay, so what's the pH of a buffer? Remember, in a buffer, we have both weak acid and we have conjugate base. So we have both of these. Okay, so how do we do this? Remember Le Chatelier's principle? It's Le Chatelier's principle. We do a moles table first, which I have the whole thing done here for you, but I'm going to do this one. I'm trying to figure out where I can do this to show you the moles table one more time. So we have our weak acid, right? I forgot a C, I forgot an H. So there's our weak acid. And then we have our conjugate. It's really hot in here. My brain's just not going to work that well. And we have our base. And just because my moles table was set up like this, it doesn't really matter at this point. Like they don't have to be in order. Those are just the 3 we have. So what do we have here? So we have, and again, this is a moles table. So we have 2.5 times 10 to the negative 3 moles of this. We added 5 times 10 to the negative 4 moles of this. The question is what happens? So remember, if we, I'm gonna just erase this for a second. If we add this, it's gonna react with this and make more of this. Think Le Chatelier's, right? So our base is gonna react with our acid. So this is gonna go, well, this is gonna be gone because we're gonna react all of it. That's gonna be gone. And then we're gonna have none left, right? Our acid, we're going to use up 5 times 10 to the negative 4 of our acid, right? We're going to use up that much. And then when we do that, we're going to make 5 times negative 4 of our, this is going to go up by 5 times negative 4. So I guess you could say plus 5 times 10 to the negative 4. I do my moles table a little bit different than like the book does. And so this one, we just subtract it, which ends up being 2 times 10 to the negative 3 when you subtract it out, right? So I'll show you a nice moles table, and then I'm going to do it using Les Chateliers again. So if we add this, it's going to react with this. So this is going to go down by the amount. This will go up by the amount. And that's what happens with our moles, right? So it's, however, we did this last class. So if you're like, wait, what with the moles table? You need to rewatch the lecture from the last class. It should help. Remember, moles table is not an ice table, but the pH in the excess acid region is determined as you would determine the pH of a buffer. Remember, pH of a buffer, this is when we can use Henderson-Hasselbalch. Can you use an ice table? Sure can use an ice table, but who would want to do that? Let's use Henderson-Hasselbalch. It's easier. And in Henderson-Hasselbalch, you can use moles. You don't have to go to molarity with Henderson-Hasselbalch. So that's a nice thing. When you use Henderson-Hasselbalch, you don't have to go to molarity. Okay, so here's our formula for Henderson-Hasselbalch. So we have to get our pKa, and remember our Ka, literally memorize this, is 1.8 times 10 to the negative 4. So we just need to take, remember P means take the negative log of whatever's after it. So we just take the negative log of 1.8 times 10 to the negative 4. That's 3.74 plus the log of our conjugate base, 5 times 10 to the negative 4 over our acid, 2 times 10 to the negative. I feel like there's something wrong with my math right here. Let me just put this in the calculator. 2.5 times negative 3 minus 5 negative 4. No, it's 2 times 10 to the negative 3. Okay. And so when we do this, I'm going to have to put this one in my calculator. 5e negative 4 divided by 2e negative 3 is 0.25. What's so hard here? The log of 0.25 is this. Whew, sorry, like literally 100 degrees in my office. And you finish it off and you get 3.14. 3.74. Okay, so when oh, that's my pKa. So my pKa is 3.74. Oh, that's where I got my 3.74. Okay, and then with so much heat here, this in here, and we get 3.14. All right, so, and again, we can do this with our moles, or we can do this with our molarity. Either or, doesn't matter, whichever one works. I feel like there's something wrong with my math here. Right? Somebody put this in your calculator, because I feel like there's something wrong with my math. Log of 5e negative 4 divided by 2e negative 3. I feel like I'm gonna need another parentheses. Yeah, I got 3.14. This is wrong. This is supposed to be 3. Yeah, for some reason I feel like there's something wrong with my math, but it works. Look at it again, 2e negative 3. It says a 5 right here, but it's not 5, it's 3. And I got 3.14. All right, so this is my pH. So you can see, I'm just gonna go back, I'll be right back to this one in a second. My pH started at 2.37 initially. I added a little bit of base. When you add a little bit of base, it's a buffer where you have both acid and conjugate base. So you can use Henderson-Hasselbalch. And so our pH went from 2.7, whatever it just was, I already forgot, to 3.14. So our pH is increasing, which makes sense. We're adding a base. Okay, so the pH in the excess acid region is determined as you would determine the pH of a buffer using Henderson-Hasselbalch. Okay, now we're going to be at equivalence point. I'm just going to tell you, I'm going to make this at equivalence point. So when I add 25 milliliters of NaOH, how do I know I'm at equivalence point? Molarity times liter equals moles. Here's my volume. There is my molarity, and I get my moles. Every single time you have to look, where are the moles? Like, where are the acid moles? Where are the base moles? Every single time you see a problem, you got to look where the moles are. Okay, so if you see, our base moles are the exact same as our acid moles. So we are at our equivalence point. The pH at the equivalence point is determined using the Kb of the conjugate base of our weak acid. Again, this was the last question on your quiz from Monday. One of the quizzes, the quiz where you actually have to do the Kb of the conjugate base. Okay, so if we look at our equation, we're going to add this many moles. Again, got to do a mole table, right? So when we do this, all of our NaOH is going to react with all of our weak acid because they have the same number of moles, which means the only thing we have left is this, right? All of our base was going to react with all of our acid. So here's the amount of acid we had. Here's the amount of base we had. All we have left is A minus. It's all reacted. So how do we find the what is this? It is this. So remember, when we write this, now this is literally exactly the same as one of the questions we did at this point in time on your quiz. The Na, we ignore it. We take CHO2 and we put it in water and we say, hey, what's that make? Well, it's a base. Base is gain. So it must be HCO2. I feel CHO2. Yeah, just making sure. Forgot the H. It's really, really hot in here. CHO2 plus, if that's a base, this is an acid. Acids lose OH minus. So our ice table is going to be this, this, and this, meaning our X is going to be an OH, right? So this is a base. So our X is going to be OH. And we have to use Kb. Two things. X is OH, got to use Kb. And that's what I mean by this part. The pH at the equivalence point is determined using the Kb of the conjugate base. So we've got a whole nother reaction that's occurring here. Here's just the reaction. Oh, so much neater. Okay, so now, since we're doing Kb of a conjugate base, you can't do Henderson-Hasselbalch. You can only do Henderson-Hasselbalch if it's a buffer. This is not a buffer. It is Kb of a weak base. So therefore, we have to do an ice table. If we have to do an ice table, we have to do molarities. Okay, so remember, we added 25 milliliters, right? We added 25 milliliters of NaOH. It was on a prior slide, but I'm not sure it went. We started with 25 milliliters this. So we had 25 milliliters in here, and then we added another 25 milliliters. So now our volume is 50 milliliters. I would say the most common mistake once people get good at these is forgetting this part. You got to check your volumes because you started with 25, added another 25, which means our total is now 50 milliliters, right? So when we do our molarity of this, right, molarity is moles over liter, it's 2.5 times 10 to the negative 3 moles over whatever 50 milliliters is this liters. I just do 10 to the 3, it makes my life easier. Less mistakes if I can just put it straight in my calculator, 10 to the 3, right? That's going to be our molarity, not the 25. So you have to add the volumes, which I think I did that right here. So here we are, I'm adding the volumes, right? My acids plus my base. So my new molarity is this. Now we can do an ice table. So not molarity divided by 2. Molarity is always moles over liters, and our liters are 25 milliliters plus 25 milliliters, right? So our total is 50 milliliters. So if it had been like 25 plus 35, then it would have been 60 milliliters. So it's always whatever your volume is. Okay, so here's our new molarity. This is what we're going to do and now we're going to put this in an ice table, right? And our ice table is going to consist of these things, right? So now this next part right here, again, this is like exactly what your, and again, I'm going through this part a little fast. This is what your quiz was on Monday, right? So for your ice table, we have 0.05 molar of this. We don't have any of this. We don't have any of this, right? Whew, so hot, right? So when we do this, it's a little bit backwards. This is going to be mine. Obviously, I was a little tired here. This is going to go down by X. Sorry, plus X plus X. This is going to go down by X. You can see my ice tables. Okay, this is driving me crazy. I did my ice table backwards, but I can't undo my ice table. So I'm trying to get a place where I can put my ice table on here. Nope, I can't. So my ice table is a little bit wonky, but it still works because I have my HA. You can see here's my HAs right here. Here's my A minus right here, and here's my OH. Some reason I flipped the two of them, but again, it doesn't matter. This is minus X plus X plus X. And so our KB is going to be X squared over 0.05. KB, again, this was on your quiz on Monday too. This is KA, but this is a base. So I need to change my KA into my KB, right? That was like on your third page, the top question, K to KB. So I cannot use this number. I must use KB. How do we go from KA to KB? 1 times 10 to the negative 14th divide. Okay. Which I have right here. Right? You literally just divide by 1 times 10 to the 14th divided by whichever one you have. And this was on your quiz, the third page top question. Okay. We got our KB. So now we can do our problem, right? So here's our KB. Now we can do KB equals X squared over 0.05, right? Multiply by 0.05. Multiply by 0.05, and then take the square root. And will X's small work? Totally should. This is -2. This is -11. On your exam, I would let you say the difference is 9, 10 to the 9th. X's small will work. I'd be okay with that. But you better check because there will be X's small that doesn't work. Okay, so we plug in our KB. And again, we assume our X is small. And we get 1.7 times 10 to the 6th. Now again, this is OH, right? This is our OH. So negative log of this is our POH, right? So we have to take 14 minus whatever we get. So in my calculator, I just do it all in one. In my calculator, I literally just put 14 and I hit minus negative log of 1.7 times 10 to the negative 6, right? Because again, had to use KB because this is a base, X is OH. If it's a base, base. Everything has to be a base. X is a base, KB is a base, right? POH base. So now at the equivalence point, I can't remember what I got. I finished this one already. At 8.23. At the equivalence point of a weak acid, strong base, you find the pH for using Kb of a conjugate base. Okay. Yes, Elizabeth had a great question. I'm gonna do this again. So I had 25 milliliters of this, and I had 25 milliliters of this, right? All of this reacted with all of this, or I should really not do it with milliliters. I should do it with moles. 2.5 times 10 to the negative 3 moles of this, 2.5 times 10 to the negative 3 moles of this, right? So at the equivalence point, the moles of acid equals the moles of base. So that's how we know what our equivalence point. So since these are both equal, they are both going to react and they are going to make this. So they're going to make all this. So now, and water, but we're not going to talk about water. So now we have to say, okay, well, what does this do when we put it in water? The Na is a non anything to us, right? Comes from, we don't look at, if it comes from a strong acid or strong base, we just ignore it. So our Na, so we just ignore our Na and it becomes CHO2. We put this in water and that becomes our new problem. And because this is a base and it makes OH, that's why we did and use the Kb of the conjugate base of the weak acid. So that's why this problem changed. And so at equivalence point, when you have a weak acid and a strong base, you're always going to be using the Kb's of that conjugate base of the weak acid, because all of our acid reacts with all of our base, and what it makes is our conjugate base. Again, the Na is not important to us. Think net ionics, not important to us. Okay, does that answer your question and clear some things up of why we went to our ice table from our moles table? Yes, hopefully. Okay. Any questions on anything here? We're good? Okay. Now, we're going to do an example after the equivalence point. So we did an initial pH. We did before the equivalence point. Then we just did at the equivalence point. Now we're going to go after our equivalence point. So again, so we have our acid that's sitting here, and all we're doing is we're continually adding more OH. And as we add more OH, our equilibrium problems change. So now I'm going to do one after our equivalence point. We just figured out that at 25 milliliters, we were at our equivalence point. So when we add 30 milliliters of NaOH, we're definitely after our equivalence point, right? Now, again, to figure out where we are, we got to find moles. Molarity times liter equals moles. Here I am, liters times molarity equals moles. So how many moles of NaOH do we have? We have 3 times 10 to the negative 3 moles of NaOH, which is more moles than our acid. So this tells us, yes, we are after our equivalence point, but we have our acid and we have our base. We've got some of both. Okay, but this is a strong base, which is going to be important in 1 second. So the pH after the equivalence point is dominated by the excess strong base. Because the base of our the basicity of our conjugate base is so small, we can ignore it. So this brings us back to like a week and a half. I don't even know. Do you remember when you were doing the pHs of two weak acids, and we decided that we only have to use the stronger of the weak acids, and we can ignore the other one? Same thing here. So I'll go back and I'll show you. What was the Kb? I think it was 5.6 times 10 to the negative 11. And that's going to become important in 1 second. Okay, so we got our moles. Now we're going to do moles table. So for our moles table here, we have 30 milliliters of our NaOH, or 3 times 10 to the 3 moles, negative 3 moles. And we have 2.5 times 10 to the negative 3 moles of this. Well, you can see we've got more of this. So we're going to use all of this, right? We're going to use all of this. This is also, it's going to go down by this amount. It can't go down by more than this amount because it all gets used up here. So at the end, we have no acid left, and this is going to go up by the amount. And again, this moles table up, up, down, that was our last lecture. So if we, again, if we add this, this is going to decrease and this is going to increase because this is going to react with this, making more of our product. Okay, so we just did this one. 5 times 10 to the minus 4, 2.5 times 10 to the minus 3. So that's our new moles. But again, unless we're doing Henderson Hasselbalch, we can't use moles, we have to go to molarity. So here's the point, here's the important part. So we have 5 times 10 to the negative 4 moles of a strong base. We also have 2.5 times 10 to the negative 3 of a weak base, but the KB of this base is 5.6 times 10 to the negative 11th, and this one is strong. So because it's so strong, we can literally ignore this. It's just like when we did our mixtures of our acids. If you have one that's much, 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 much weaker, you can just ignore it because it literally negates it. And it literally makes it so it doesn't dissociate at all. So we can ignore it. And then we just have our pH of our strong base. But again, we got to go to molarity. Can't do it in moles. pH only works in molarity. So here's where we are. Now remember, we added 330 milliliters to our 25 milliliters. So again, don't care about this. I'm going to ignore it because it's so weak it doesn't matter. 5 times 10 to the negative 4, so if I want my molarity, over 25 times 10 to the minus 3 liters plus 30 times 10 to the minus 3 liters. That's just the way I turn my stuff into liters. I just multiply by 10 to the negative 3. Just the way my brain works. So this is going to be the molarity of our base. So the molarity of our base equals 0.09. 9. Let me put this in the calculator, make sure. 0.09. 909. That's the molarity of our NaOH. So now we just need to take the negative log of this, subtract from 14. Strong base. That's our molarity. So 14 minus negative log of 0.00909. It's our pH. So when we do that, 14 minus negative log of 0.00909, we get 11.959. That's what I got when I did this one. So the pH after the equivalence point, just gonna erase it so it's all nice. Oh, did I not do my molarity right? Oh wait, it doesn't matter. This molarity doesn't matter. Yeah, 11.96, 959.96, close enough. It should be 959 with sig figs, right? 11.959 with sig figs. It should be 11.959. Again, this molarity of nacho, you don't even need it. So once you've determined to when you're past the equivalence point, the strong base is so much stronger than that weak base, you can just ignore the weak base. Okay, so when you have a weak acid, strong base after the equivalence point. How do you know you're after the equivalence point? Your base is greater than, your moles of your base are greater than the moles of the acid. That's how we know we're past our equivalence point. At that point, the only thing that matters is the molarity of our base. Remember, when we find the molarity of our base, we have to take the 25 milliliters and the 30 milliliters into account. So there's a lot of little pieces here, like a lot of little pieces. Okay, any questions on this part? Oh, they did their pH here a different way. So I do pH, so that was a good question, where the H3O plus come. I do pH this way, 14 minus negative log of the OH concentration. That's the way I do pH. You could have done it the longer way, where you use your KW to get to pH and then do negative log. I just did it a different way when I wrote it out. You can do your pH whichever way you choose. I just like it this way. So this is just the alternative way of doing pH. But you see, no matter which way you do the pH, you end up with the exact same answer. So whichever way you like better, you can use. I just feel this one's shorter. I like that one. But whichever way is fine. Okay, so in summary, adding NaOH, strong base, to our weak acid. We started with a pH of 2.37. This was initially only weak acid. So we did the Ka of the weak acid when we got this one. Now, after we added a little bit, we had a buffer. We used HH. So before our equivalence point, with a little bit of base added, we found our pH using a buffer, HH, Henderson-Hasselbalch. Oh, this part's we're going to talk about, we didn't do the half neutralization, but we'll talk about that one in a second. We'll come back to this one later, the half neutralization point. Okay. Now, after we added 25 milliliters, so here we are adding 25 milliliters. At this point, our moles of our base equal the moles of our acid. And we found this pH doing the Kb of the weak base. And then when we did 35 milliliters, which we didn't do 35, right? I thought we did 30. It's probably this one right here. We did pH. We did it using pH of a strong base. So in this one problem, 3 different ways of finding the pH. pH of a weak acid, pH using a buffer, Henderson-Hasselbalch, pH using a weak base with Kb, pH of a strong base, right? So it's 4 different problems, all in one little piece. Okay, so any questions on this? I'm going to talk about a half equivalence point, which is a super fun part. Just a second. Okay, so there's this thing called a half equivalence point. And so at your half equivalence point, which looks like it's about 3.74. You can't really see it. So this is about our half, so here's your equivalence point. When you're at half your equivalence point, it's when your pH equals your pKa. And it has kind of a special thing, and use Henderson-Hasselbalch there because we're in the buffer region, right? So at the half equivalence point, pH equals pKa, and we'll do one of those in just a minute. So I'm going to just color these regions for you right now. Ka of a weak acid is right here. That one doesn't really get a lot of color. Buffer, when do you use buffer? Here's when you use a buffer. You're never really, you could be over there. Here's when you do KB of your weak base. And here's when you use, maybe not green. Here's when you do pH of a strong base. So at the initial, KB, weak acid. Equivalence point, KB, weak base. Before equivalence point, buffer, Henderson-Hasselbalch. pH of a strong base after the equivalence point. At your half equivalence point, your pH equals your pKa. And that's called the half equivalence point. Also, I want you to notice this. Look at, I'm running out of colors to use. Look at the pH right here. pH at equivalence point of a weak acid, strong base is basic. pH at the equivalence point is basic for a weak acid, strong base, right? For a strong acid, strong base, remember the pH was 7. Strong base, weak acid, pH is 8. Okay. So again, just as a review, these are just talking about the problems we did. Initial pH, Ka, weak acid, just like when we were doing Kas and weak acid. Before the equivalence point, buffer, Henderson-Hasselbalch. The half neutralization point, that's when the pH equals the pKa. That's just a special fun one, which we'll look at in just a minute. Beyond, so now we're going to go to at the equivalence point. At the equivalence point, weak base equilibrium problem. Beyond the equivalence point, OH strong base, like strong base OH. Strong base pH problem. Like I said, these are a lot, right? It's, like I said, it's every single thing we've done in one problem. Okay, so now let's go to a weak acid, strong base. Again, let's try it. Okay, this is a problem. So this would be a problem like you would see on a quiz. 40 milliliters is a sample of 0.1 of your nitrous acid, weak acid. It's titrated with 0.2 molars of strong base. Okay, so in your brain you go, oh, this is weak acid, strong base titration. Okay, calculate the point at equivalence point. Okay, so what's the first thing we need to know? How do we find equivalence point? Equivalence point is where the acid, moles of acid equal the moles of base. Okay, so here's our basic problem, right? We have our weak acid, our strong base, right? I just wrote it in, like, I didn't include the N, the K in the products because we don't even care. So we have to figure out, we want to know the volume at the equivalence point. So this question is literally like, it's when the moles are the same, right? So if you have 40 milliliters, which is, I don't even know, 40 times 10 to the minus 3 liters. And your, this is going to get too big. You can literally just stoichiometry this one. It's kind of nice. And this is NaOH. No, it's not. It's HNO2. So hot in here. So our molarity. So there's only really one. We have this molarity and this molarity and this volume, right? So we kind of have to deal with these two. So that's our NaHNO2. So we have 0.1 moles for HNO2. 1 liter. 1 mole of HNO2 to 1 mole of KOH. I'm literally just going to stoichiometry this. So in order to, what I'm doing is I'm saying if I have 0.1 molar of this, and there's 40 milliliters of it, and I have 0.2 molars of this, what I want to do is, if I use all of this, how much of this do I need? I want the volume of this. See, this looks like a Chem 219 or Chem 209 stoichiometry problem. If I have this, I want to know how much volume of this to do. So then I have 0.2 moles of KOH per 1 liter. And you get, I don't know what you get. 0.02 liters of KOH. So that means when we add 20 milliliters of KOH, we will have reached our, thank you, 20 milliliters, we will have reached our equivalence point. Because remember, when moles of acid equal moles of base, equivalence point. And so with this one, it seems like you're like, oh my gosh, but when you're like, what about this problem? But this is a problem you've actually seen a ton before. This one reacts with this one. How much volume do we have left? It ends up just looking like a, oh, okay. Nope, can't erase that. There you are. And so it ends up being 20 milliliters. So it seems like it's going to be a titration problem, but when you set it up and you use, I always say, if you have this balance equation, use this balance equation, right? So always make your balance equation. It's going to help you figure out where you're going and what you're doing. Okay. Now we have a 40 milliliter sample of 0.1 molar HNO2 is titrated with 0.2 molars of KOH. Calculate the pH after adding 5 milliliters of KOH. Okay, so I bet anything we're before the equivalence point here. Like, educated guess, yes. Again, first thing we notice, weak acid, strong base. Okay, so in our brain, we have to go, okay, weak acid, strong base. And we have to know the rules. How do we find the pH? Before, or initial, before, at, after, right? There's going to be different ways to find the pH at each of those times. So we have to figure out where we are. How do we figure out where we are? Got to find our moles. So first thing, got to figure out how many moles is this? Molarity times liters equals moles, right? How many, okay, it's 0.004 moles. Now we need to figure out how many moles is this? We just multiply them. It's 0.001 moles. Okay, we have less moles of KOH than we do, or we have less moles of our strong base than we do our weak acid. We must be for equivalence point. How do we find the pH before the equivalence point? And then in your brain, you have to go, oh, I'm not sure, right? So before the equivalence point, well, let's look at it. So let's make a moles table. Let's say you're like, I don't remember how. Okay, so then we'll just make a moles table. So if we have, and sometimes I do my moles table like on my equation or in the table. I'm just going to do it in the equation right now. So I have 0.004 moles of this, right? And I have 0.001 moles of this. So this is going to go down by that amount. This is also going to go down by that amount, but this is going to go up by that amount. So I'm just applying Le-Chatelier's here. Right? So that means I'm going to end up with 0.003 moles of this and 0.001 moles of this. Oh, look, that's my conjugate. This is my weak acid. Oh, it's a buffer, right? And so again, here's my moles table, just me doing it in a table. But we realize we've got conjugate acid, we have weak acid and conjugate base. So this is a buffer. Henderson-Hasselbalch. Whenever I see Henderson-Hasselbalch, it makes me so happy because I don't have to do an ice table. So love not doing ice tables. Okay, any questions on this part so far? So when you start your pH problem, you got to decide, well, what kind of problem is it? Okay, It's weak acid, strong base. Okay. Then you're like, where am I? Am I before the equivalence point? Am I at the equivalence point? Am I after my equivalence point? What do? Gotta look at the moles, because remember, when the moles of acid equal moles of base, you're at the equivalence point. In this case, our moles of our base were less than the moles of our acid. So therefore, we are at before the equivalence point. Then we're like, okay, well, what happened here? Well, I'll use my moles table. We had this much, and then it reacted. It went down by 0.001 molar, and this went up by 0.001 molar, and this went down by this. Now, how do we know that this is a buffer? Remember, a buffer is the weak acid, HA, and its conjugate. So if we have both the weak acid and the conjugate base, then we have a buffer. Here is our weak acid, here is our conjugate base. That makes this a buffer. And a buffer means we don't have to use an ice table. By the way, you can use an ice table with a buffer. You just don't have to. So we can use Henderson-Hasselbalch. So in Henderson-Hasselbalch, what do we have here? We've got here's our same moles table we had before. Remember, when you do Henderson-Hasselbalch, you don't need to do molarity. You can just do it straight with moles. You can do it with molarity, but you don't have to. You'll get the same exact answer, so it literally doesn't matter. So the Ka for this one is 4.6 times 10 to the negative 4. And remember, for Henderson-Hasselbalch, it's the pH equals the pKa, and then plus the log of the conjugate base over the acid. So I think of it as like, some people say, aha. I think of it as base over acid, like ba, like a sheep. So we just need to take the negative log of this and plug it in here. Here's our conjugate. That goes here. And then this one goes here. And we get our pH, right? Okay, so, and again, what I'm doing right now, this is what we did. I think we did this on Monday. I can't erase all this, so I'm just gonna have to erase this because I have this here. So when I do my pKa, for some reason, I calculated this wrong and I can't fix it. It's not 3.15, it's 3.34. And then when you do the pH, you get 2.86 when you plug it all in. So again, how did we know it was a buffer? Weak acid and conjugate base. So we had both our weak acid and our conjugate base. That's how we knew we had a buffer. All right, any questions on this one or where we are? So really all we're adding to these titrations is we're just taking everything we had and we're just going, okay, so I do this type of problem here. Okay, I do this type of problem here. Okay, I do this type of problem here. This is why I said that quiz that you just took is super important, that you really understand all of those questions. I posted the key up there because it's all of these types of questions, right? I don't think there's a Henderson-Hasselbalch. That one's coming this week, right? The Henderson-Hasselbalchs are all coming this week. Okay, or not this week, Monday. All right, let's try another one. A 40 milliliter sample of 0.1 molar weak acid is titrated with 0.2 molar strong base. Calculate the pH at the half equivalence point. Now remember, half equivalence point, that's when the pH equals the pKa. Right? So when you see half equivalence point, pH equals pKa. Which means also we have half the amount of moles. So how do you say this? So the moles of our base are at half the amount of moles of our acid. So that means here's the moles of our acid. So at the half equivalence point, that means we would have half the amount of this. So we'd have 0.00200 moles of NaOH. So pH equals pKa, and moles of base equals half of acid. So those two things are true at the half equivalence point. And of course, I just wrote that down. So if we do our moles table, and again, I'm going to do my moles table up on my equation just because my brain thinks that way, but I'll also do it in the actual table. So that means if we start with 0.004 moles of this and 0.002 moles of this, that means all of this is going to get used up. And half of this is going to get used up. And this is going to go up by that amount. So I'm employing Le Chatelier's. If I increase this, this decreases, and this increases. Just Le Chatelier's. Okay. So that means I'm not going to have any of this left. I'm going to have this and this. Oh, sorry, that was wrong. I'm not going to have any of this left, and I'll have this and that. And they'll both be the same. So now I have my HA and my A minus. I have both of those, 0.2 molar of each of those left, because this is all gone because we subtracted it out. And for your moles table, a lot of people like doing it like this. I'm absolutely do it like this. My brain, for some reason, just likes to be in the equations, but whichever way works best for you, as long as I can see how, as long as I can follow your work, we're good. Just like that one question where people got it completely wrong, like so wrong, but really like the answers were completely wrong. But the only things that you forgot to do is you forgot to do your molar mass for chlorine because it's diatomic. It was 70.9 and you put 35.5, but it messed up the entire problem in the quiz. But that was the only mistake you made, so you lost barely any points. So again, as long as I can follow your work and figure out where your mistake was, you won't lose a lot of points on your exam. Okay, so now at our half equivalence point, our pH equals our pKa. And again, here's our moles. It's just the same moles table as before. Here is my pKa, and my pH should equal my pKa, right? So what should the pH be? It should be 3.15, because that's the definition, 3.15. When you plug in the numbers, you know what you get, 3.15. Because try it, put it in your calculator. The log of 1 is 0. So this ends up being 0. So at the half equivalence point, your pH equals your pKa. Okay. That's just a fun little piece now. Okay, so now, what about if we have a weak acid? I'm sorry, a weak base and a strong acid. So in this case, you're going to see that means we have the weak base in the beaker. And we're going to add the acid to the beaker. So initially, all we have is weak base. So guess what? Kb, weak base, right? Here's our equivalence point. I'll come back to our half equivalence point here. We're going to talk about this one. Here, we're going to have a buffer, right? This one, it's going to be, you're going to see it ends up being Ka. And then this one's going to be excess acid. It's literally, think of it as the exact opposite of what we just did. But I also want you to notice, and you're going to see in just a second, when you have a strong acid and a weak base, the equivalence point is acidic. Strong acid, weak base, acidic pH. Okay, so we're going to do the same thing again. We're literally just going to do it the opposite way. So we're going to start with a weak base and a strong acid. The initial pH of a weak base strong acid is using Kb of the weak base because, well, we don't have anything else but a weak base. So we would find our pH doing Kb of weak base. So here's what we've got here. But again, right now, all we have is this in our beaker. So that's all we have in our beaker. We write our initial equation, right? But again, all we have is our weak base. And remember, how do you know how to do this? If this is a base, bases gain. This is an acid, acids lose, right? So that's how So this is when I talked to a lot of you that you make like that you're making little mistakes. And I said, if you can do this, it's really going to help you, because on your ICE table, I don't have the nicest ICE table, right? On our ICE table, right, we have 0.1 of this, none, none, right? This is going to go down by X. This will go up by X. This is going to go up by X. And so this is 0.1 minus X, X, X. Here's your KB and your PKB. So my KB, again, has to be KB because this is a base, which is 1.8 times 10 to the negative 5 equals X squared over 0.1. Assume this is small. It should work. This is 0.1. This is negative 5. Difference is negative 4. X is small should work. We could check it, but it should work. Multiply by 0.1. Multiply by 0.1. And take the square root, right? And we get X is equal to 1.8, no, 1.3 times 10 to the negative 3. But remember, this is OH, because this is OH, because this is the base, so this is a KB. All three of those things are true if we've got bases. So when we do this, you can either do your 10 to the negative 14th kW. I just like to do 14 minus negative log of 1.3 times 10 to the negative 3. That's why I like to do my pH, which I don't know what that is. Okay, 14. Any questions on this part so far? So initial pH, KB of the weak base. There it is. So here's my ICE table. And we get 11.13. And I solved it the long way with the pH, but you end up with the exact same answer. So you can either use KW or KW to get to K, or just find POH. I just like to do POH and subtract. So this problem right here is just like the one you did on your quiz. Okay, so now we're going to go before our equivalence point. So guess we're going to add a little bit of acid now, just a little bit of acid. So 5 milliliters of acid, just a little bit of acid. Now again, first we need to determine. So in this case, I'm telling you, we're going to do it before our equivalence point just to show you, but you need to figure out where we are. How do we figure that out? Find our moles, right? We got to find our moles. Our initial moles, molarity times liter. Here's our initial moles. Then we need to figure out, well, how many moles did we add? So when we do that, again, how many moles did we add? We have 0.1 times 5 times 10 to the negative 3. I don't know if I have this on here. 0.1 times 5 e to negative 3 gives us 5 times 10 to the negative 4 moles of HCl. Well, we've got less acid than we do base. So therefore, we are before our equivalence point. So since we're before our equivalence point, we can do a moles table. We need to see like what changed here. Okay, so we have, and I'll do a moles table regular, 2.5 times 10 to the negative 3 moles of this, and 5 times, I should have left more room, 5 times 10 to the negative 4 moles of this. I'm going to use all of this. It's all going to go away. So this is going to go down by that amount, and this will go up by that amount. I'm just going to do a moles table to make it easier. Oh, yes, there's my moles of HCl. Okay. So now we need to do our mole table. So our mole table, again, we're going to use all of our acid is going to react with our base. So our acid is going to go down by that much, our base will go down that much, and our conjugate will increase by that amount, right? And so here's our ending moles. So notice this. This is a buffer. Yay, but it's a basic buffer, different than an acidic buffer, right? So again, there's two different ways you can use Henderson-Hasselbalch here. You can either use it as you can use the acid way or the base way, but you need to decide which one. This is a basic buffer. We can still use Henderson-Hasselbalch regular, but we can't use the pKb. We have to turn it into a pKa. Okay, so we have to turn it into pKa if we're going to use Henderson-Hasselbalch and go straight to pH. You can go to POH and subtract. Absolutely, we did that. Yes, last class we did that. So you can do that, or you can just do it the regular way. So remember Henderson-Hasselbalch for the pH, it's pKa, right, plus the log of our base over our acid. This is why I always say base over acid, just because then it's interchangeable if you've got a basic buffer or an acidic buffer, base over acid. But this has to be pKa because they gave us pKb. We have to turn our pKb into a pKa. How do we do that? Just 14 minus it. So this is our pKa. That's our pKa. So we're going to have 9.25 plus the log of our base. So we have to put our base on top, which is 2 times 10 to the negative 3 over our acid, 5 times 10 to the negative 4. And again, you can do this with molarity, but you don't have to. So let's see here, 9.25 plus the log of 2e negative 3 divided by 5e 4 parentheses, and I get 9.85 for my pH. Now again, you could have done it with the molarity, but you don't have to with Henderson-Hasselbalch. So with Henderson-Hasselbalch, you don't have to. You can just leave it in moles because the volume is the same for each. So when you divide them, they cancel each other out anyway. So I just leave it in moles for Henderson-Hasselbalch. Makes my life easier. I don't do this last step if I have Henderson. Again, how did I know this was a buffer? Weak base, conjugate acid. Don't care about the CL. Conjugate acid. Weak base, conjugate acid, buffer. Buffer means I don't have to do an ice table, right? You can do an ice table, it'll work. Just makes math icky, but you can do an ice table, but you don't have to. Okay, so now what if you went to the molarity? I'm going to show you get the same pH. So if you go to your molarity, see I got 9.85 for the pH here, right? And you plug all this in, but you plug your molarity in instead, you end up with the exact same pH. I mean, 9.85 is the same as 9.84. Just some maybe sig figs went a little crazy. Okay, questions on this part? So again, before our initially KB weak base, before our equivalence point, basic buffer. Okay, so you gotta do basic buffer. Now we're gonna do at the equivalence point. Again, remember at the equivalence point, acid equals base. Moles of acid equal moles of base. So our moles of acid we've already determined is 2.5 times 10 to the negative 3. So that means our base is also 2.5 times 10 to the negative 3. Now when we make our moles table, this is 2.5 times 10 to the negative 3, and this is 2.5 times 10 to the negative 3. This is all going to react. The only thing that we're going to be left with is our conjugate acid. That's all we're going to be left with is our conjugate acid. You don't really need to know the volume. It doesn't matter, right? Because this is going to go down by that much. This is going to go down, and this is going to go up by that much. So that's all we have here. So if all we have is our conjugate acid, and we put it in water, Remember, if this is an acid, acids lose, bases gain. We're going to do the ice table. It's going to be Ka of weak acid. That's what we're going to use our Ka and our weak acid to figure out our pH. And our X is going to be H3O plus. But this is moles. We need molarity in our ice table. Our molarity has to be in an ice table. Okay, so again, when you do your molarity, it's 25 milliliters. Oh, that's why we had to find, and 25 milliliters. We had to figure out what the volume was that we added. That's why I did this part. And again, how do we do that? Just stoichiometry. So to get our molarity, we had 2.5 times 10 to the negative 3 over 25 plus 25, well, 50. Which is 0.05 molar. And again, this is the molarity of our NH4 plus. Now we can start our ice table. You're like, now we can start our ice table. Yay. Oh, here it is. Here's where we get our molarity right here. So the pH at the equivalence point is going to be using our Ka with our weak acid. And so this is our number we're going to do to make our new ice table. So our ice table is going to be, again, here's the equation I just drew on the other slide. Here it is again. So our ice table again, ICE. I just do that with my water, right? So what do we have here? We have 0.5, was it 0.05? Yeah, 0.05. 0.05 this, none of this, none of this. This is gonna go down, this is gonna go up, this is gonna go up, x 0.05 minus x, I'm gonna ignore that. So again, this is acid, so I need Ka equals x squared over 0.05. Oh, they gave me pKb. So I need to change this pKb into a Ka because it's an acid. Again, how did I know it's an acid? Because I wrote the equation. It's an acid. So 14 minus my pKb equals my pKa. I don't even know what that is. 14 minus, it's very hot in here. 14 minus 4.75. 14 minus 4.75. So my pKa is 9.25. Now to go from pKa to Ka, remember P means take the negative log. So I just take, and to get rid of that, right, we just 10 to the negative 9.25. 10 raised to the negative 9.25 gives us our pK, which is 5.6 times 10 to the negative 10th. Sorry, this is our Ka. So I couldn't even start the problem until I got my Ka, and I had to change it. So my Ka is 5.6 times 10 to the negative 10th. Gonna have to have all your ducks in a row with these problems because there's a lot of little pieces. That's why I've been working up towards these. And you solve for your x, and I'm just going to tell you what your x is here. You can do the math from here. 5.3 times 10 to the negative 6 after you solve for your x. And x is H3O plus, right? X is. So we can just take negative log of 5.3 times 10 to the negative 6. Negative log 5.3 negative 6. And I get my pH is equal to 5.28. And I'm at my equivalence point. So I've got a strong acid and a weak base. At the equivalence point, I should have an acidic pH. All right, questions on this one. We still have to do after the equivalence point, which is really easy. It's just the pH of a strong acid. It's like super easy. pH of a strong acid. Okay,